Good morning, everyone.
Good morning.
We are very happy to start with you a new webinar in the framework of the Capacity Reinforcement Program implemented by the International Energy Agency on energy data and modeling for Ethiopia. So today we will spend 2 hours together and we will mainly discuss modeling topics, and we will illustrate how to do modeling on the demand side with the building sector. So today I will be joined by my colleagues Ariane and Tim, who will come later, and I propose just to show you uh, where we are in our online training. So yesterday we had the sessions on statistics, energy efficiency indicators, prices, and taxes. Today we will move to the modeling part of the training, building, and then we'll go to other sectors, as you can see here on this agenda. Housekeeping rules. So we will use live poll. So please connect to www.menti.com because we will have a few questions we ask to you. If you have a need for an urgent clarification while we do the presentation, please raise your hand so that we can stop and explain more. If you have questions, you can use the Q&A box, and you can also raise your hand. So if you want, you can speak. And if you have additional questions you want to send later on, you can reach out per email, of course. So today we'll discuss energy modeling. And as some of you may recall, we had a specific session to introduction to energy modeling last summer. So I will just give a few recalls of the fundamentals of energy modeling. Then you will hear Ariane and Tim explaining more the activity, the structure, and the performance of the building sector, and how they model it, and how they look for driver in this specific sector. Then they will explain step by step how they move from estimating useful energy to final energy demand, and with a critical step, which is allocating technology and fuels. And last, we will also present to you a few key findings on the building sector. But before we enter into that, we wanted to start with the first online poll. So we invite you to go to Menti. So if you have a smartphone with you or another computer, just go to internet, write www.menti.com and enter the code that you can see here on the top of the screen. So the code is 67357286. And the first question we would like to ask you is, when we look at sub-Saharan Africa today, to you, what is the largest fuel which is used in the residential sector after traditional biomass? So I give you some time to answer. So for those who might just join now, please go to www.menti.com, enter the code that you can see on the top part of the screen, and answer to you what is the largest fuel used in the residential sector after traditional biomass. So we propose several fuels: electricity, oil, gas, coal, modern use of biomass, or solar thermal. Maybe to guide your thinking, you can try to think in the residential sector, what are the energy needs? Why do we need, what do we need energy for? And this can help you maybe guess what will be the type of fuel of energy that can meet this need and this demand. I can see that some people are answering in the Q&A box. We really ask you please to go to the website menti.com so that we can see the answers of everyone, and we can, it's a bit like as if we were in the same classroom. Okay, so maybe I can, we have answers on oil and coal. The right answer actually is electricity, because today when we look at the residential sector in sub-Saharan Africa, by far, and the first fuel used is biomass. It's 83% of the energy needs in the residential sector, mostly for cooking needs. And then the second fuel is electricity. And people use electricity in the residential sector to power appliances, to get lighting, etc. Oil can also be used, especially when there are some backup generators which work with diesel or oil products. In some countries, coal, especially in China, can be used as well for cooking or for space heating. So it's also important. But in Africa, the first one is biomass, and then it's really electricity. So moving to another question. So this was today. Now, if we look ahead in the future, which fuel do you think will account for the majority of the final demand growth? So we're looking at the growth between today and, let's say, 2040. Which fuel will have the fastest growth, or the biggest share of the growth in energy demand for the residential sector? Do you expect electricity to be the fastest growing fuel to meet energy demand in the residential sector? Oil, gas, coal, solar thermal? Okay, so we already have a few answers, and you expect electricity to be the fuel that will most grow or meet the final demand growth. And in all our projections, that is the case. So, of course, no one knows what the future will look like. We can only make assumptions and try to predict based on several scenarios. But in all our scenarios, we expect electricity to grow most. Solar thermal has also a huge potential for water heating, especially in sub-Saharan Africa. Okay, so thank you very much for your answers. We'll come back to the presentation and start by recalling a few fundamentals on energy modeling so that we are all on the same page. So energy models are tools which are not perfect tools, which are not crystal balls, but what they do is that they are used to ask questions from a given perspective. But then when we think about the future, there are different ways of positioning ourselves. We can try to do forecasting. So this is to say we want to try to predict what the future is likely to be given a certain set of assumptions if some conditions are met. And we can also have a strategic or planning approach where it's quite the opposite. If we want to have reached several objectives by that time. For example, if we want to have universal access to electricity and to clean cooking by 2030, if we want to be aligned with the Paris Agreement climate goals, what is the policy way, what is the pathway to get there? So these are the different type of scenario and attitudes towards the future. When it comes to the energy model and the tools themselves, when we want to estimate the demand for energy and how it will evolve in the future, we can have a top-down approach. So, quick example, how will evolve the demand for oil products in the transport sector in Ethiopia in the coming years? A top-down approach, which is based on econometric relations, would look for relations between socioeconomic drivers and our variable activity. So we could say, let's look how GDP per capita is related to the fuel consumed in the transport sector. And if we know how GDP per capita is supposed to evolve in Ethiopia in the coming year, we can estimate how this will reflect in terms of evolution of the oil consumed by the transport sector. So this top-down approach enables to do quick estimation. It's very well adapted to the short term, but it's not super accurate. This is why there is another approach, which is the bottom-up one. And here, what we try to do is really to disaggregate the energy sector we are looking at, and really to try to understand technology by technology, what are the drivers and what can drive the evolution of the energy demand. Again, taking the example of estimating future demand for gasoline in transport in Ethiopia, what we could do is, okay, let's look at the transport sector. We know there are cars, there are trucks, there are buses. We know they have different efficiency levels. The motors are not the same. We can try to estimate how people want to move and to be transported, how much goods need to be transported, so how many kilometers they will travel, how many people will there be in each car. And at this very disaggregated level, we can try to make some projection, and then we come up and see how this will reflect in the demand for oil products. So this is takes a lot, much more time, but this is more accurate, and it really relies on knowing very well the technologies, so the efficiency levels of the different cars, etc., etc. When it comes to estimating the supply of energy, we have different ways as well. We can do some optimization, saying, okay, we want to maximize the quantity of electricity which is supplied under certain constraints, like we can put as constraint CO2 emissions, etc. So this is the first way to make projections on how electricity can be supplied. And we can also do simulations. For example, we can use the price signal and see how consumers and producers would react to a certain price. If we assume that the oil barrel would be at $50 in 2030, how much oil will be consumed at that price, and how much oil can be produced by companies, by producers at that price. So this is an iterative process that we can work on. Keep in mind that to do energy modeling, we need to build scenario, and we need to take assumptions. And what is a scenario? Is just a coherent storyline with sets of policies that describe a specific pathway. At the International Energy Agency and in the World Energy Outlook, we have different scenarios. One is a stated policy scenario, which really is to simplify, is a business as usual or projection of what today's policymakers have taken as action and intentions, so announced policies. But we also have a sustainable development scenario, or even an Africa case. The Africa case is a scenario where African countries meet the development goals of the Agenda 2063 for economic development. Plus, we have energy access in full by 2030 and improvement of air quality. So here, the scenario is built on a strategic planning way where we say we want to have reached those targets by that time, and we define what is the pathway to get there. Doing energy modeling requires to take assumption, and at the IEA we have a wide source of data, internal and external. It's very important to be transparent and to make public your assumptions and to have peer review and experts review those assumptions, for example, cost of technology. And then we have exogenous assumptions that will be inputs to the energy model, like socioeconomic drivers, GDP, population, but also policies, like we will take into account if the Ethiopian government has set a target for energy efficiency. We'll also have assumptions on the technologies, their cost, their constraints, their ability to be deployed at a certain pace, etc., etc. This is a simplified view of the world energy model, which is the model we use at the IEA. And this chart might look complex, but we will come back to it often because it enables to put on one slide all the steps and all the subsectors we are looking at. So on the top part, you can see the assumptions, which are inputs to the model. So we'll have policies, technologies, socioeconomic drivers, we just discussed. And this will enter into the model where, if we go from right to left, we will have the different energy sectors. So we disaggregate industry, transport, building, and we disaggregate even more, looking, for example, for industry at the steel production, the cement production, all the typology you have seen in the previous statistic course. Then, once we know the final energy demand, we can look at the transformation processes. So once we know how much electricity is needed for buildings, for services, for industry, we can look at how electricity will be generated from different primary sources. And we have the primary energy demand for hydrocarbons, but also for hydro, for example. And going further left, we will have the supply side, so supply of fossil fuels, import, exports, and trades. And this is where the prices for fossil fuel play a role of equilibrium. So let's look more at the building topic. On this figure, you can see energy, the evolution of energy demand and CO2 emissions in the building sector. As we mentioned, in the building sectors, the energy needs are broad. We need energy for cooking, for space heating or space cooling, depending on the weather where you live. We need energy for powering some appliances. And much more. So this reflects in a wide diversity of fuels, which are highly dependent on the region of the world. So you can see that there is a big use of bioenergy, mostly for cooking in emerging and developing economies, and specifically in sub-Saharan Africa. But you also have heat, electricity, gas, oil, and other. So these are the historical data. From there, what the future could look like. And here, no one has the answer. We need to take a scenario approach. And this is where energy modeling can be very insightful for policymakers to understand what type of futures lies ahead. So in our steps stated policy scenario, where we reflect the announced policies, we see that the demand for energy in the building sector is set to increase by 30% to 2050, and emissions of CO2 would also increase. And electricity takes the lion's share of this increase. But if we take another scenario and the sustainable development scenario, we see that emissions reduce sharply, and we also have a decline in the use of certain fuels in the energy sector, in the building sector. So looking now a bit more, having a more focus on sub-Saharan Africa. Here you have the total energy demand for the residential sector in sub-Saharan Africa, excluding South Africa, in 2018. So you can see that the final consumption needs in the residential sector for oil and natural gas are mostly for lighting, appliances, and also for cooking. And the need for electricity is mostly for lighting and appliances. So what the future could look like. In our stated policy scenario, we expect a very sharp increase of the energy demand in the residential sector. And you can see that the demand for oil and natural gas would mostly be directed to water heating and cooking. And this can mean more LPG for cooking, for example, or natural gas for cooking as well. Whereas the demand for electricity in residential sector would able to meet the needs for lighting, for powering appliances, but also space cooling with air conditioner. This is the first scenario. In a second scenario, you can see that the result would be different with drivers to this growth, like a higher GDP would reflect into a higher energy demand. More people getting access to both clean cooking and electricity will also have an impact and increase the energy demand. But we can have efficiency gains and reduce the demand. For example, having more efficient cooking devices, having more efficient lighting bulbs like LEDs instead of standard lighting devices. Looking now at Ethiopia, more specifically, you can see on this chart, so you still have fossil fuels on the left and electricity on the right, but here we are looking at the entire final energy consumption. So this includes all the final sectors, productive use or industry, transport, and residential. And you can see that residential has a small share of the final energy demand today. But in 2040, this is to increase, but we also see that transport energy demand would double, and this will reflect in a higher demand for fossil fuels. We expect in Ethiopia by 2040 to have 700,000 cars on the roads. When we look at the productive use, we would see that it would triple both on fossil fuel needs and electricity. And looking at the residential sector will also entail an increase of energy demand because of more people living in cities, people having more appliances, people having more energy needs. And we can see that the use of fossil fuel would increase by maybe 6 times, the use of electricity by 8 times. But if we go to our Africa case scenario with everyone having access, for example, and higher GDP, we can see that this demand is even higher. So I will stop here for this first part of introduction, and I would like to show you some a presentation by Ariane, who will present more the activity of the building sector in its own.
On this slide, you have the general schematic overview of the World Energy Model. And in this presentation, we will focus on the building sector, which includes the services and residential sector, which are encircled in red on the slide. You can also see the main driver of the related energy sales demand. When looking at this overview, we should not forget that an important additional feedback needs to be considered: the impact that electricity and heat prices and fossil fuel prices have on end-use demand in general, and in this particular case, on the energy demand in the building sector. When working on the sector, the first step before doing any modeling is to analyze what do people want. What they want and use are called energy services. In the building sector, it can be space heating, cooling, lighting, cooking, etc. To meet service demand, we need energy, and this energy is consumed by different technologies. In the building sector, it can be air conditioners, light bulbs, radiators, etc. And for each equipment, we also have its associated efficiency. We therefore can distinguish three areas: activity, structure, and performance. The activity is linked to the energy services. The structure is linked to the type of equipment present in the building sector, and the performance is linked to the efficiencies of the different technologies. And all of this needs to be depicted in the model. If we look in more details at the structure of the building model, we see that we have different parts that make up the model. The first part includes all the inputs that are needed to do the modeling: historical data regarding energy balances, building stock, equipment sales, and also socioeconomic data like population, electrification rate, or GDP. And we also do some assumptions for the evolution of some of these data, so for instance, population. Some of these inputs will be used to compute energy service demand drivers, like household occupancy, floor area, or appliance ownership. Of course, these drivers will differ for each subsector. Indeed, the drivers are then used to determine the future useful energy demand, or the activity, as mentioned earlier. So for instance, for space heating, we can use the floor area as one of the drivers. In addition to that, we also need a number of historical and future technology data that describe the structure and performance of our system. These data include the efficiencies, the lifetime, the market share of the different technologies. We can then compute for each end use what technologies will meet the service demand, and we will finally estimate the energy demand by subsector and by fuel, as well as the investments and CO2 emissions. If we look in more details at the structure of a building model, we see that we have different parts that make up the model. The first part includes all the inputs that are needed to do the modeling. As we've just seen, we need a lot of data inputs, as data are essential for energy models. Accurate balances are the basis for all modeling work, as we have seen and mentioned in the previous webinars on energy statistics. That's why it's important to build a data repository to organize all the data that you will use for your modeling. As mentioned, the data include energy balances, technologies data with efficiencies, costs, but also policy data that will impact the evolution of this sector. We will explore which are the most important ones in the next slides. As mentioned earlier, one important step of the modeling process is to define energy demand drivers, as they play a key role in describing energy consumption patterns in energy models. Thus, it's crucial to define the best proxy to describe past trends and possible future ones. Before looking in detail at drivers and different methodologies to estimate them, you can see here the general structure for modeling end-use sectors. So first, with the drivers and econometric analysis, we estimate the evolution of the energy service demand, or useful energy. Then, to meet the service demand, we allocate different technologies. And in the case of the world energy model, we use a cost-based approach to do this. Then, with the efficiencies of the different technologies, we can compute the final energy demand. If we go back to the drivers, we will look over the next slides at possible methodologies to identify the best proxy for each subsector. The projections of activity variables can be based on regression with respect to GDP or electrification, but we can also use different types of curves, like the S-curve. And as mentioned earlier, this requires to use different data that can come from the IMF or other national reports.
You've now been introduced to the importance of buildings energy demand modelling and the strong role of bottom-up modelling of energy demand for each end use within the building sector. And then following this, the processes and structure used in the modelling of buildings energy demand in the International Energy Agency. And now I'd like to focus in on one of the most important steps of our modelling process, and that is the definition of the best proxy to then describe the activity variable that can help us understand how service demand evolves for each type of building end use. So again, the proxy is the link that helps us to go from socioeconomic information to activity variables and then to services demand. Now, why do we need this link? Well, firstly, activity variables, we might have this information available for certain countries in the historical period, but we don't have it available for all countries over all of the time series, and we definitely don't have this information available for the projections. So therefore, it's up to us to take the information that we do have, and that is socio-economic information, and to use this information and these assumptions for the future to calculate our own activity variables. Once we've calculated these activity variables, we can use them in our projections to understand how service demand evolves, and then based on what technologies we choose, how energy demand evolves in our projections. Now, there are several types of activity variables that are of interest to us. Certainly in the building sector, one of the most important activity variables is household occupancy. So this is how many people live in each household on average. Now, household occupancy can help us to understand energy demand for end uses such as cooking or water heating, for example. Now, because we do not have information on household occupancy into the future, it's up to us to try and define a relationship between a variable that we do have information in the future and this household occupancy variable. So here we've chosen to plot values of household income against household occupancy. So we've taken all the data on household occupancy that we do have for historical periods for different countries, and we've put them on this chart against the GNI per capita, which is in itself an indicator of household income or of personal income. And what we can see is we have an inverse curve that's being drawn here. So that means that as we increase the average income per capita or per household, then we are decreasing the number of people per household. So here we're seeing a strong relationship between GNI per capita, so gross national income per capita, and a decreasing number of people per household. So we have on the right an inverse curve equation that can be used to define this relationship, and then can be very interesting for us and is a key step in our modeling to be able to say in the future, if from our external assumptions, which for us come from organizations such as the International Monetary Fund, the World Bank, and our own assessment and projections of economic growth and population. We then use these assumptions on economic variables to understand via this equation how household occupancy evolves in time. So that's just one example of this process of identifying a proxy that has a good relationship with the variable that interests us and using this proxy to describe the activity variable. So here, household occupancy. Now, another example of a relationship of interest to us in the buildings energy demand modeling area is ownership variables. And so how does the ownership of a given appliance, such as a refrigerator in this example, evolve in time based on another variable? So here we've plotted ownership of refrigerators for all the countries for which we have data and over all the years for which we have data. And we've plotted that against here where we have a discriminant criterion, but we can very easily say that we can plot this against GNI per capita or even GDP per capita. So the most important variable to have on the x-axis is income in this case. And if we build this chart and fill out the data, we can very clearly see that there is an S-curve relationship between refrigeration ownership, so the average number of refrigerators per household, and the average income. And so that means that with time, as income increases, then we get to a point where the number of refrigerators on average per household starts to really increase. And then as we get to a point where households are increasingly rich, then the growth in refrigerator ownership slows down. Because once we get to a point where we already have at least one refrigerator on average per household, then obviously there's less need to increase and to continue to purchase additional refrigerators. So there is a saturation point, and that's why S-curves are so important, because they show us at the start that we might not have enough income even to think about buying a refrigerator, but at a certain point we start to cross that threshold and a refrigerator becomes a desirable and useful purchase and use of income. So we see that growth, that increase in the rate of growth of the S-curve, and then it flattens out as we start to saturate. So the S-curve is a very important indicator for understanding the relationship between many economic variables and the activity variables that interest us for buildings energy demand modeling. And I'll get to a description of the discriminant criterion and how we can draw upon several economic variables to influence and describe this curve in just a minute. But firstly, I would like to go through an example of air conditioning ownership. So here we've done the same thing as in the previous figure. We've plotted on the left-hand side, on the y-axis, the average ownership of air conditioners, and on the x-axis, the average income per capita. So we've used all the data points that we have in our database, and we can see that it's a big cloud of points without a very strong relationship. So here it's difficult to imagine an S-curve describing the evolution of air conditioner ownership with income. But when we bring an additional piece of information to the picture, we start to see much clearer relationships. So now we start to plot data points, so air conditioner ownership and income, depending on the need for cooling in that region. So here the need for cooling is described in terms of annual cooling degree days. So a cooling degree day is a variable that can be calculated based on the threshold temperature in a given country and the average daily temperatures within that country. So here we can clearly see that for countries in darkest red, so the countries with the greatest cooling demand need, there is a relatively strong view of an S-curve that evolves in time. So we can see that as in those countries incomes start to increase, the rate of air conditioner ownership rapidly increases and moves towards 1, so an average of 1 air conditioner per household. However, if we look at countries in blue, so with very low cooling needs, then we can see that even when incomes, average per capita incomes increase to very high levels, the air conditioner ownership stays quite low, because obviously these households, despite their high incomes, are prioritizing purchases in other needs because their cooling needs are not very high and not very pressing. So the message here is that sometimes we might have just the economic variable, so GDP per capita, and some information on ownership, but that's not enough to define a clear trend and a clear curve that can be useful for us. So sometimes we need to bring additional data to the table to help us understand the evolution and the relationship between the economic variable and the activity variable that interests us. Now, before going on, I'd just like to summarize some of the key end uses that we model in a bottom-up fashion in our buildings energy demand modeling, and the activity variables that we use to describe the energy service demand for that end use. And then further on, the proxy that we use, so the economic variable that is a key variable for us to help to understand the relationship between evolving economic conditions and the activity variable. And then finally on the right, the type of curve and the type of equation that we use to connect the proxy with the activity variable. So firstly, with cooking, the first curve that we saw was an inverse curve. And so for cooking, we use people per household to help us understand the evolution of service demand. So people per household is our activity variable. And as with all end uses in buildings, we're using GNI per capita, or you can use GDP per capita as well, as the most important proxy to help us describe the evolution of the activity variable. So we take our projection of GNI per capita that comes from other assumptions. So again, it might be World Bank, IMF. For population, it might be the United Nations. And then we use this variable via the curve, so the inverse curve in this case for cooking, to describe people per household and understand the evolution of people per household in time. For lighting, we use an S-curve because the activity variable is floor space per household. And with an S-curve, that describes the fact that as households become more rich, so does the floor space of those households increase, and then we get to a point where there's saturation, and so the S-curve starts to flatten out. For water heating, it's again a question of describing energy service demand by the number of people that live in the household, because if we think that each person in the household may take 1 shower per day, therefore the energy demand need for water heating is dependent on the number of people in the household. So here, again, we're using an inverse curve, the same as for cooking. But then if we look at air conditioning, so cooling and appliances, then it's a question of ownership. How many air conditioners or how many refrigerators, televisions are owned on average by the household? And then how does this ownership evolve based on increasing income? So again, an S-curve, rapidly increasing at a certain point and then starting to slow down as ownership saturates. Now, just a note here on cooling, we could also say that floor space per household is an important variable, because if we're trying to cool a much larger household with 1 air conditioner, then we're going to be having a higher energy service demand. So we can certainly look at both variables, firstly the ownership rate, and then also if we have an increasing number of meters squared per household, that will also increase the floor space, the energy service demand, sorry. So in cases like this, we can look at having 2 activity variables that both combined can help us to understand the evolution of energy service demand. Now, to move on, I wanted to come back to the fact that sometimes we want to bring in additional variables to help us describe the trends. So if we look on the left-hand figure, the x-axis here is just GNI per capita. So it's an income proxy, essentially. So we're taking our income variable and we're using this to describe the number of units per household. But we can see that the curve is quite cramped. It's really not an easily defined S-curve. And that's because in the first, let's say, $5,000 of GNI per capita, there's a huge amount of people that suddenly buy refrigerators. And it's all happening very rapidly, and perhaps economic variables such as GNI per capita are not the perfect variable to understand what's happening in this first part of the curve. But now if we turn to the right-hand side figure, then we can we use here a discriminant criterion. So this is basically saying it's a It's a variable without a unit, which is just an indicator that combines several proxies. So it's combining GNI per capita, so it's taking the economic variable, but we're also bringing in information on the electrification rate within the country and the urbanization rate. Because when we start plotting this data, we clearly see that not only does the economic variable influence ownership, but so does electrification rate and urbanization. Because obviously we're not going to buy a refrigerator if we do not have access to electricity. So despite the fact that we might have an income, if without electricity, there's no point buying a refrigerator. So this is, it seems evident, but obviously it becomes very important when we start translating it into these curves, and we can see this flat period at the beginning for those that still don't have access to electricity, despite the fact that they might have an income. And likewise, the data shows that with higher levels of urbanization, we also have higher levels of refrigerator ownership. And so we bring in these three different variables that describe so an energy access trend, an economic trend, and a geographical trend, and bring that information together to build this discriminant criterion, which then helps us to get a much more clearly defined S-curve, which is then more useful in understanding in the future with a given a value for energy access, for income, and for urbanization, what might we expect in terms of ownership. So this is multivariate analysis and multivariate regression, as opposed to the earlier examples which were shown, which were using a single variable, so GDP per capita in those instances. Okay, now let's run through the principles of multivariate analysis for using many or several economic variables, population variables, or other interesting variables for which we have information to describe the evolution of activity variables. So the first point here is to look at the data that we do have. So taking the data we have on, say, if we're interested in refrigeration ownership, looking at the available data on refrigeration ownership, selecting a set of these data points which seem like a good, clean trend, and then trying to match these data points with available variable data on, say, GNI per capita, GNI per, or GNI absolute values, electrification rates, weather data perhaps, or any other variables that might be available. And then what we can do is plot all these variables together on a chart. And so, for instance, we'll have our variables on the y-axis on refrigeration ownership, and then we'll be plotting that on the x-axis against lots of different variables again and again to try and understand, is there a relationship between that variable refrigeration ownership and the variable that we're putting on the x-axis. And so what we can do, what we achieve by doing this, is we identify the most important variables that seem to have some sort of relationship between this variable and refrigeration ownership. And then we can partition the data into similarities, or based on what the data is actually describing. So for instance, if I take GDP per capita or GNI per capita, they're very similar data points. And so within this multivariate process, there's no point having data points that overlap and describe very similar trends. So even though both GNI per capita and GDP per capita are very useful variables that can both be used to describe the evolution of my activity variable, I'm not going to put them both into this multivariate analysis because they are describing the same things. However, if we look at a variable such as electricity access, then that is removed from GDP per capita and describing a different set of trends, and therefore we would put that in another class, and it would be very useful then to have variables from different classes, for instance 2 or 3 variables from 2 or 3 different classes, and bring these together to then feed into to establish the best combination of these descriptive variables that can be used to describe our activity variable. So once we have the 3 or the 2 variables that we've chosen, then we want to use a certain type of multivariate regression to understand what the best combination of these variables is to best describe this activity variable trend. So for us, we use canonical variate analysis. And so that's something that, that you can look up and try and understand the processes involved, or there's many other multivariate regression techniques that can be used to combine several variables to deliver one discriminant criteria, so one variable that combines all this information and then can be used for us to plot and understand the evolution of the activity variable. So that's then step 5. Once we have this relationship defined, then we can use our projections of, say, electricity access rates, of urbanization, of GDP per capita, feed all this information in, calculate our discriminant criteria, then take the discriminant criteria, put it into our curve equation, so our S-curve equation in this case, and then that will give us a forecast of the ownership of the activity variable. Now, the final point I want to make before I pass on again here is what we do with tracking data and how do we project the variables that interest us when we do not have the available historical data. So to take a step back, the first thing we do is we bring all the data that we do have together for all the countries that interest us. And then what we'll do, we'll divide the countries into different classes based on the type of, I guess, the category of the country. And so, for instance, we would bring countries together that have similar economic contexts, that have similar climatic and population growth contexts. So here on the left, we can see we've put countries, so country A, B, and C into different classes. And so we have several different classes for countries across the world. But for instance, if you're looking just at the African region, it might be pertinent just to have one class and to not bother about defining different classes. Now, once we've done that classification by class, then we need to look at the data availability for each country within each class. So for instance, if we take the example of country A, then country A is a country that is well informed in terms of data. So we have historical data available for many years for the activity variable that interests us. So it could be household occupancy, it could be refrigeration ownership rates, it could be floor area per average household. So here we have the information we need historically to be able to build the curve, build a robust equation that then can be used for the projections. However, for many countries, this unfortunately isn't the case. We do not have this data available. So for many countries, we find ourselves in the position of country B. So that means we're poorly informed. We might only have a couple of data points. So there might be a data point from a survey that's taken place only once, or maybe 5 years ago and 10 years before that. And so that means that we don't have sufficient data available to build a robust and reliable curve, so an S-curve equation, for example, and then to be able to use this S-curve equation to project activity variables into the future. And so what we do in this case is we use the curve that was described by all the countries for which we do have data. So we take the average curve of all the countries in class 3. So for instance, if we put all the data for ownership of refrigerators for countries in class 3 together in one figure, and then we use that to describe, to build an S-curve, and we have the equation for that S-curve, we can then use that S-curve equation for all countries that find themselves in the position of country B. But we shouldn't forget that for country B, we do have 1 or 2 data points. So what we'll do is we'll then shift the curve up or down to make sure that the curve is running through the most recent historical data point that we have available. So that's a way of ensuring that for us, we can use these curves to describe the trends for the 1 or 2 data points we do have, and to backfill the missing historical data, as well as understanding how these activity variables will evolve in the future. The final situation is the situation of country C. So this is a country for which we have no data at all for activity variables for the end use that interests us. So in this case, we have no other options. All we can do is take the average curve of class 3, so the average of all the countries within this class. And so that means country C will just be described by the average throughout, because we don't have any data points to be able to shift and run through those data points. And so we go straight through to the projections of the activity variables using obviously the economic variables that are specific to country C, but using the S-curve or the inverse curve equation, that is the average of all the countries in class 3. So this is a very important point on how to find the data and then what to do with the data, and what to do, very importantly, when we don't have the data, all the data that we need to build these curves and therefore to project the activity variables. And just a point to note on data, so obviously there's many different sources available for countries across the world, but in many African countries, it can be quite difficult to find this sort of data. So at the International Energy Agency, we've often looked to surveys such as the surveys conducted by USAID, and we can find these surveys online, the DHS surveys, and often there is information within those surveys that can be used to help us in this modeling process. Alternatively, there can be specific literature on a specific country based on surveys conducted within that country, or based on academic work. But basically, the first step certainly is to look for the data that does exist for the end users that interest us most, and to contact or reach out to as many people as you can to try and get the best data and ensure that you start with the strongest foundation.
Okay, so we can come back to the presentation, and I would like to open for questions from the audience. So again, you can use the Q&A functionality to write your question, or if you want, you can directly raise your hand. We'll be very happy to give you the floor. So as you have seen, when we want to make projections and to try to anticipate what the future energy needs will be in a specific sector, and here we're looking at the building one, we really want to have a sophisticated approach and to try to understand the drivers. So if we look at cooling, what will drive the need for cooling? What are the activity variables we are looking at? Is it the number of AC units? And then how can we estimate how this number of AC units will evolve in the future? And this is where we have done a bit of math, looking at relations and doing some curves and formulas that we will enter more into details during the exercise. I give you a bit more time to ask your questions. Okay, if you don't have, and while you are writing your questions, and again, please feel free to raise your hand. I do have questions for you, so I propose we shift back to Menti, where I would like to hear from you on more specific topics. So if you go back to the Menti website, www.menti.com, you still have the code here on the top part of the screen. So it's 67357286. And here, what we are asking you is thinking of the most important parameter to estimate total demand for cooling. So assuming that you know the energy consumption of one AC unit, what would be the most important parameter then if you want to make projections and estimate the total demand? Is it the floor space? Is it the number of households? Or is it the number of units, of AC units per household? So maybe to specify, what we would like to estimate is the total demand for energy consumption in a given country, assuming that we know the energy consumption of one AC unit. Okay, so we are gathering a few answers. Well, first, I'd like to say that there is no wrong answer or right answer. Actually, all those parameters are important to make this estimation. So looking at each of them, the floor space will be an important information to know how much household will want to use their AC units. If they live in a small room, it's not the same as if they live in an important home. So floor space is definitely a key information to understand the intensity of the equipment that we will have on average. Then the number of units per household is also very key, because this is how we'll estimate, we will get to understand how much consumption per household we will have. But we also need the number of households in the country to multiply and then to get the total number for a given country. So those three parameters are very important to make this estimation. Moving to another energy need, if we look at water for showering, for example, assuming that you have the energy consumption of a water heater in a house, what is the most important parameter if you want to estimate total demand for water heating in the country? Is it the floor space? Is it the number of households? Or is it the household occupancy, so which is defined as a number of people living in the household? So from the previous question, you may think that the three are the correct answers. We'll see in a second what are the most important parameters. So actually the right answers are the number of households and the household occupancy. The floor space is not a very relevant indicator when it comes to assessing the need for water heating, because regardless of the size of the house, the most important parameters are more how many people live in the houses, because if you assume that one people takes one shower a day, this will reflect in energy demand. And then, as previously, we need the number of households to multiply and get the number at the scale of the country. So thank you very much for your answers. We can go back to the presentation, and I see that we have some questions. So I'd like to take a first one, and in the last part of this webinar, we will have Tim and Ariane also joining, and they will be able to give more answers. But the question received is, how can we consider the human factor? I mean, the personal preference matters to the energy projections and in modeling this behavior. So this is an excellent question. I think, as you have seen, we touch a bit on that. For example, when looking at the ownership rate of appliances as a function of the income, and this is where you had the S curve. So we, based on the historical data we have on a number of countries, we can the numbers we have reflect somehow the behaviors and the personal preferences. For example, when income increase, people will tend to buy new equipment. So one phone, one refrigerator. But as the income is even increasing, we reach saturation. And it's not because you get richer that you will buy 5 refrigerators. So in historical data, we have historical behaviors which are reflected, and we can take them into account. Then when it comes to looking at new behaviors, it's something very complex, but that at the IEA we are increasingly working on. In the transport sector, for example, as we can see, for example, today in Europe with the lockdown and confinements, some people might now have a stronger preference for using their individual cars or their bike rather than going in public transportation where they are all together. This is very much related to COVID and the pandemic, but this might be a new behavior that will reflect into different energy needs. Still, with this pandemic specific situation, we also do have a strong preference for teleworking, so less commuting, people working from home, with more electricity demand from the residential sector and less use of the company buildings. So these are new preferences and behaviors we are trying to take into account. But I will let Ariane and Tim give more information on that. So if there is no more question, I propose we go to the last part of the presentation, which is really step by step illustrating how we move from the useful energy demand to the final energy demand. And last, Tim will share some findings on the building sector specifically.
Once we have determined past and projected activity variables and service demand intensity, the total energy service demand, or useful energy, can be computed. For this, we can rely on end-use intensity, which is derived from our projections of activity drivers, as well as other data coming from our database, like the historic energy demand by fuel and end users, historic and projected temperatures. So we usually use heating degree days and cooling degree days, or historical technology market share and efficiency. For instance, with all this information, we can compute the energy intensity per square meter for space heating. Once obtained, the total projected service demand, we can now reflect on which technologies will meet the demand. So for each year of the projection, we can compute the total energy service demand that needs to be satisfied by new equipment, by accounting for new incremental demand and considering the retirement of existing technologies. So of course, in later years of the projection, we also have to take into account the retirement of technologies that were added by our model. So how do we do this? For this, we need to have a detailed stock accounting. So with the historical market shares and efficiencies, we can compute the stock of existing technologies. And with the lifetime, we can determine the remaining stock for each year of our projection. And finally, we can compute the service demand to be met with new sales. So the sales of new equipment need therefore to replace previous equipment and and to meet new demand for energy services. So you can see that the lifetime of equipment and its age distribution can play an important role in the capability of the system to renew the overall technology stock. In countries with burgeoning energy demand, such as in developing countries, the share of replacing old infrastructure and technologies is more limited, while its weight is more important in advanced economies. Now we have to determine which technologies will meet the service demand. The technology and fuel choice depends on a variety of elements, and first of all on the available technologies for each subsector in each market considered. That's why we have an important database with all technologies available in each subsector. So for instance, you can look at the cooling subsector and you can see the different types of air conditioner that are in the model. The choice of technology depends on various parameters. The available potential of renewable resources can play a very important role, as well as several energy policies such as energy efficiency standards. In the World Energy Model, we rely mainly on a cost-based approach to determine which technologies will be installed. For this, we need to compute the cost associated to each technology, which includes the investment cost as well as the operation cost. For instance, for an air conditioner, we must take into account the price of this AC, but also the price of electricity that will be consumed by this technology. In our model, we assume that the technology share will be proportional to 1 divided by the specific cost of this technology. This least cost approach is often the most used criterion to select the technologies, but it's also important to consider boundaries to reflect market failures, behavioral patterns, and energy policies. For instance, we can set a minimum target for heat pump to be installed if we consider that energy policies are pushing the development. Here you have an example of the projections we made for various lighting technologies. On the left, you have the evolution of efficiencies, and on the right, the evolution of the market share of the LED. So with this information, we'll be able to compute the main outputs of the model. So you can see that estimates of historical efficiencies and performances of equipment and possible future evolutions are key parameters to make reliable estimates. That's why technology partnership, sharing information, and continuous interaction with the energy industry are really crucial elements to achieve it. As said before, once the technology choice is determined for each subsector for each projection year, together with the market share, efficiency, and fuel of use, the final energy demand can be computed, as well as the related CO2 emissions and the investments that are needed for new equipment additions.
In the last part of this building's energy demand modelling session, I would like to provide several examples of the results of our modelling, specifically the results of our modelling applied to the Africa context, and use these results to reinforce the importance of efficiency gains and understanding the impacts of improving efficiency and changing technologies on energy demand. So these are some of the results that we can then communicate to policymakers to reinforce certain messages and the importance of taking steps and putting in place policies to achieve energy objectives. So here we've taken an example from the International Energy Agency's World Energy Outlook Special Report on Africa, published in 2019. So looking at electricity demand from household appliances in in the year 2040 under two different scenarios. Now, if we look at the left part of the figure, we can see that under a scenario where the current and announced policies are enacted and economic growth follows an expected trajectory as announced by the International Monetary Fund, then we could see electricity demand across Africa for these uses, for residential uses, increasing to around 350 or close to 400 terawatt hours. However, if we pass to a scenario where economic growth in Africa is much more rapid, so economic growth is in line with the expectations for African countries, and we also have energy access, so universal access to electricity and to clean cooking, which is achieved by 2030, so in line with the Sustainable Development Goals, then we see a much more rapid growth in energy service demand. So obviously, if we come back to the activity variable story and the bottom-up modeling process, then higher economic activity means higher average household incomes. This then translates to greater floor area on average per household, much higher household ownership of appliances such as refrigerators, televisions, washing machines, and higher household ownership of cooling equipment such as air conditioners. So if we just added to the system the same equipment that was being used in the step scenario, then we would have a huge increase in electricity demand. So going from around 350 terawatt hours to over 1,000 terawatt hours. So this obviously has very important implications for power systems and for the costs needed to increase generation capacity, increase transmission capacity, and then for energy bills, electricity bills for consumers. But what we want to show here is that by improving the efficiency of the appliances that are added, we can drastically reduce the impact of all these additional appliances. So that means that we can have a big increase in demand for energy services and so in quality of life because people have more appliances, but we've limited the impact on the energy system. So that's through greater efficiency. And so if we look at the right-hand side of the figure, we can see that the very important differences in the ownership variables for different types of appliances averaged across Africa. So we can see that we have significant growth already in the steps, especially in appliances such as televisions and refrigerators, but also in air conditioners, although they do remain at a much lower base. However, if we look at the Africa case, then this growth in ownership really does explode. So obviously this is important. It's people getting access to services, but via the modeling, we understand that as we put in place more efficient technologies, so thanks to policies, then we can limit the impact on energy systems of this increase in energy demand, energy service demand. So to be able to do this sort of analysis, we also need to have the modeling in place, but we need to understand what policies are in place today and what are the efficiencies of existing equipment and equipment being sold. For instance, we'll need to know how efficient are the air conditioners being sold today and what policies are in place that would impact the efficiency of these air conditioners. So that provides us with a baseline, and we can also look at how the policies and the policy change over the last years has impacted the energy intensity of these end users. So here is just an example where both heating and cooling policies have been tracked, and we can look at the building stock and the useful energy demand in terms of understanding which part of that energy demand is covered by policies or not covered by policies. And then based on that, we can understand how stringent is the average coverage across the building stock. And so what we want to see is that the stringency improvement really brings down the energy intensity of meeting demand for services such as cooling and heating. And if we take the example of water heating, then here we're looking at the evolution of energy demand in 3 different scenarios. So the first scenario, the RTS, is a scenario similar to STEP. So here we're just looking at the policies that are in place and the policies that have been announced, whereas the 2 scenarios to the right are more ambitious scenarios that meet climate objectives, so a 2-degree scenario and a below 2-degree scenario. So what we see here is just pure outputs of our model when we impose the constraints of saying we need to reduce emissions in line with a certain scenario, so 2 degrees or beyond 2 degrees. Then that means we need to see a big change in the fuel mix. And so this is obviously bottom up. It's coming from us saying we need to allocate a renewable technology as opposed to a fossil fuel fired technology. And these are the evolutions of the energy mix that then result. So it's these kind of results that can provide a visual communication of what the modeling is doing and then help us to bring together key messages and key numbers to communicate to the policymakers who can then act on the information coming from the model. And one final slide here is very specific to Africa and specific to cooling, to again underline the importance of increasing efficiency. So Africa's cooling needs, as many of us know, are much higher than most other places in the rest of the world. Many locations across Africa have cooling needs that are an order of magnitude higher than in countries such as France or Italy. And these cooling needs also dwarf major cooling demand centers of China and the United States today. And we see that almost 700 million Africans today live in areas where the average daily temperature exceeds 25 degrees. And average temperatures are often 1 to 2 degrees higher again in cities. And as Africa's population increasingly urbanizes, cooling needs will further grow. By 2040, the number of Africans living in hot areas approaches 1.2 billion people. As populations expand, especially in cities, and average temperatures increase with climate change. High cooling needs today and higher cooling needs tomorrow contrast with some of the lowest levels of air conditioner ownership in any region. Averaging today only 6 units, so 6 air conditioners on average per 100 households. Now, obviously, wealthier countries across the continent, such as Morocco, Algeria, and Tunisia, have higher ownership rates that can be up to 3 times the average of the African continent itself, while less affluent countries with often much higher cooling needs have ownership levels that are only half the African average or less. So as a consequence of this low average ownership of cooling needs, electricity demand for cooling today is very, very low in Africa. But the potential for future growth is strong. Ownership of cooling devices sees an important increase in our Africa case in response to these higher average incomes I described earlier and rates of access to electricity. So we reach in 2040 an average of 25 units per 100 households, but this is still well below the global average today. Ownership of fans increases further, but fans obviously have a lesser impact on electricity demand. So if we focus on electricity demand from air conditioners, then we can see that electricity demand in the residential sector across Africa for this end use could grow to well over 200 terawatt hours by 2040. So that is just a huge increase in demand that would have major implications for power systems, especially because of the fact that air conditioning electricity demand is often concentrated in certain hours of the day, so difficult to manage. But the importance here is to use the building energy demand modeling to understand that if we change the efficiency of these air conditioners, then we have the potential to cut this future growth in half. So we can reduce costs for the power system, reduce costs for the consumer, and reduce emissions. So here, this is again the messaging using the model to understand if we change certain variables, such as putting in place a policy which improves air conditioner efficiency, what are the results that we could expect?
Okay, so I hope this explanation by Ariane and team was clear. If you have questions right now, you can already write them down in the Q&A box. And what I'd like to do now is to present to you an exercise that you received yesterday. So we will look at how can we illustrate what has been said today by Ariane and team, looking at how to estimate the future energy demand from households' cooling needs. So I will show you the Excel sheet. Okay, I hope you can see well my screen. So here you had an exercise with some questions and a very simplified model where the aim is to, again, estimate what will be the need for electricity for households to meet their cooling needs. So as in many modeling sheets, what you can see is that we have historical data, and on the right part, you have projections. So we have one column per year. If you extend, you will see all of them, but here we are regrouping them. Then we have drivers with each expressed in a specific unit. And the step we will take is to go from drivers to energy services demand, looking at the efficiency of the fleet of equipment, allocate those technologies, so those equipments, and be able to deduct the final energy demand. So I will go question by question. And the first one we wanted to do is to look at the historical data, because I want to insist on that. You cannot make projections, you cannot make good estimations of what the future will look like if you don't know where we are today and where we come from. So the first question was to calculate GDP per capita in another unit, kilo USD, to calculate the average number of AC units per household and the average number of people per household. So if I look at the correction, so GDP per capita, we just ask you to go from US dollar to kilo US dollar, so just dividing by 100. AC units per household, here we have the total number of AC units in the country and the total number of households. So we just need to divide one parameter by the other. And number of person per households or household occupancy. Likewise, you were already given the total population in the country and the number of households. So this was just about doing some first easy calculation to get those first parameters. So we just copy paste the results to this part of the sheet. So question one is okay. If we then the second step we wanted to do is to make projections of the relevant drivers, because as we said, if we want to estimate the future consumption, energy consumption for cooling needs, we need to think of the drivers, that's the parameters that drive the need for cooling. And in that case, we want to look at the number of air conditioner units in the country. And to estimate it, we will rely on econometric approach, and we'll try to look for a proxy to understand how this number of AC units in the country could evolve. So going step by step, you were asked to calculate the future GDP per capita in the country. So this is same as what we just did. We have projections of the future GDP per capita and of population. This is not something we've developed ourselves. This comes from other organizations like UN population, like International Monetary Fund. So they do their projections and we can rely on them to do our work. So again, to have GDP per capita, it was just dividing to move from USD to kilo USD. So this question was also easy. Now we'll try to project the future number of air conditioning units per household. So this is AC units per household. We have just calculated the historical data. So there is 0.04 units per household in the year 2000 and 0.062 in 2019. What will this number look like in the future? So here, there are different ways of doing it. The first one could be, okay, we look at the historical data and we can try to see how it has evolved over time. And we can try, for example, to calculate an annual growth rate, which I've just done here. So looking 1 year compared to the previous one, we can see that every year this number increased by 2.5%. So a first easy way could be to take the average growth rate of the past and to apply the same in the future. And this is how we can get those numbers. So we just multiply for the year 2019, the value of 2018 with the average annual growth rate. But another thing we can do, as we've seen in the presentation, is to look for a proxy variable. And the income or GDP per capita can be a good proxy to see how the number of AC units per household would evolve. So here in this part of the Excel sheet, I have put again the GDP per capita and the historical number of AC per unit, and have put them on a figure where you can see AC units per household as a function of GDP per capita. As you can see, so the yellow dots are the historical data. These seem to be quite linear. So there is a linear equation, and if I, for example, add a trend line and display the equation, I see I have a relation of the type y equals ax plus b. So if I just take the parameters of this equation and put them here, I can make a calculation of the future AC units per household, knowing how the GDP per capita will evolve. So I just make the calculation based on this formula. So here we are projecting number of AC units per household based on the future GDP per capita. And I just put again here the numbers I got from this calculation. Okay, so question 3 is done. Then when it comes to looking at the number of people per household, we are confronted with the same issue. We don't know how the number of households will evolve in this given country, but we know how GDP per capita will evolve. So if I take again an econometric approach, here you have the values of GDP per capita, historical and in the future, and I have put on this line the estimated household occupancy as function of GDP per capita. This is not a linear curve. This is more an inverse curve. And as you have seen in the presentation, when we have this type of curve, the mathematic formula is of this kind. So here we have 3 parameters, A, B, and C, which are constant parameters that we need to determine if we want to have this equation. And here, to get those numbers, I used an Excel function, which is called the solver. So Excel will work together itself to find those right numbers, and we can show more how it technically works later on, or send some guideline on that. But basically, the idea is that we now have find a strong relation between household occupancy and GDP per capita. Given that we know how GDP per capita will evolve in the future, we can deduct how the household occupancy would evolve itself. And here we came with this type of curve, but we could have tried to, if I add a trend line, so you will see that if I add a linear trend line, maybe it's not the most accurate. Maybe I can try another type. And if I add the equation, I will have another type of equation that I can use again. So I have different parameters. So there is not one way to do it. It's just the idea that we want to get the best relations between our proxy variable, GDP per capita, and our activity variable, which is household occupancy. But doing that, I have been able to project the estimated number of people per household in the future, which I just put here. Okay, so now we have answered question 4. If we move to question 5, number of households in the country, well, this is now easy. We have person per households and we have total population. We can easily deduct the number of households. And as we also know, we have projected the number of AC units per household and the number of households. We can deduct the number of AC units in the country. So here we have done our first step, which is based on our estimation. We know that the number of AC units in the country is to go from 1.5 million in 2018 to 2.7 million in 2030. So this was our first step. Now we'll look at how much those AC units will be used in the future, because maybe if it's getting hotter and hotter, people will want to turn on the air conditioner longer in the day. So we need to have an idea of the intensity of the use of those devices. So this was question 9, looking at no, sorry, we are at step 2, question 7. So looking at the future energy service demand, and here what we had was we already knew the service intensity, so how much service we want to ask our AC units to work on, and we were asked to make a projection. So what we decided to do here was to calculate what was the growth rate over the past period. So here, this is a compound average rate, average growth rate between 2010 and 2018. And it's so we can see that it's increasing every year by 3.5%. So we just decided to apply the same growth rate in the future. And from there, we can deduct, as we know the number of units, and as we know how much service energy we are asking those units to work, we can deduct the total service demand. And this is really an important part, that we now have an estimation of, in the future, how much energy is demanded to power these equipments. Next steps is to move from future service demand to final energy demand. And here is where it comes to looking at the efficiency levels of each equipment and at the market share, or how many equipments we have in the country. So if we look at the historical efficiency levels, we were given a certain number of assumptions, like technology A, technology 1, let's imagine it's basic AC units or even fans. Technology 2 would be some intermediate AC units, and technology 3 would be super advanced AC units. And each have different level of efficiency, and those efficiency evolve over time. So those data can come from the industry, from peer review of those technologies. And here you have the historical efficiency, and we wanted to calculate the average efficiency, which will be a weighted average of those values. So, no, sorry, excuse me. On question number 9, to calculate the historical efficiency level, what we've been doing is we knew we had historical data on the electricity demand and on the total service demand, so we can deduct what is the level of efficiency of, on average, our fleet of AC units. So this is how we can calculate those values of the average efficiency. And later on, we'll enter into the specific efficiency of each technology. So yeah, this is the step we're coming on now. We have the average efficiency, we have the specific efficiency of each technology. Now, so we need to understand how many fans we have in the country, how many intermediate AC units, how many super advanced AC units we have. And this is then translated in market shares, like the number of units in the total fleet of equipment. And as we know that the average efficiency needs to be a weighted average of the efficiency of each technology by its market share, we can deduct the market share of each technology. And we are also told in the question that the technology number 3 is not yet deployed in the country before 2018. So now we can see that we have only 2 technologies which are developed and deployed in the country, and they have their respective market share. Now that we know better those market share, we can see how those market share will evolve in the country. Ariane was mentioning that we can do that on a least cost analysis. Fans are cheaper, so people are likely to buy more fans than the super advanced AC units. But this is where policies come into the game, because if there is strong support, for example, subsidies or other incentive for people to buy the most efficient technologies, then it's possible that we can increase the share of those technologies. And here you were given assumptions that the technology number 2 will increase at a rate of 1% per year, and that technology number 3 will reach 7.5 market share in 2030. So we entered here those parameters, 1% decrease for technology 2 and 7.5% market share by 2030. And then we can deduct what will be the remaining market share for technology number 1. This being done, we can project what will be the average efficiency level, because we know the efficiency of each technology and we know how it will evolve. We know the market share of each technology, so we can do a weighted average and know what will be the average efficiency of the fleet of cooling devices. And from there, it's now easy to calculate what is the electricity demand, so the final energy demand, because we know what is the total service demand, and we know the efficiency, the average efficiency of the equipment, so we can deduct the electricity demand. So this was the end goal of the exercise, knowing and making by making hypotheses and calculations how the final electricity demand for cooling in the residential sector could evolve. Now, what we can do is to try to do sensitivities analysis. And here, if we look at some charts where we will see how the total electricity demand is evolving in our model, we can see that if we change parameters, there will be an impact. For example, we assume that household would use every year a bit more their AC units, and that this growth rate will be 3.5%. What if people use it a bit more and it's 4%? We see that it translates into a higher increase of the total electricity demand. We were at 0.32 terawatt hour in 2030, and we went up to we were at 0.35, and we went up to 0.37. But in parallel, if we push more for the technology number 3, which is more efficient, so if the government puts a target of having 20% market share of this technology by 2030, we see that we come back to 0.35. So people can use more and have more service if if the average efficiency of the fleet is better, and if there is if there are a higher deployment of the most advanced technology, this increase in the service can be stable and not translate into an increase of the total final electricity demand. I stop here, and I will send you in a few minutes the correction with the Excel file, so you can take more time to look into the answers. And with that, I'm happy to open again the floor for questions and answers. And I see that I'm joined by Ariane, who you have heard presenting some parts of this presentation. So we are very happy to take any question. Please use the Q&A box, and you can also raise your hand and ask your question. Hello, Ariane.
Hello.
Maybe, Ariane, a first question I've started answering, which is about the human factor and behavior in estimating future energy demand. So I start mentioning that we have historical ownership rates that can reflect human choices. For example, there are saturation levels when a household gets a certain number of equipments. But maybe can you touch a bit more on some behavior changes in buildings that would reflect in specific impacts of energy demand?
Yes, sure. So, as Arno mentioned, we can play on the appliances equipments, but there are also other end users that can be impacted by behavioral change. So, for instance, the temperature setting for cooling or heating can change due to behavior. There are also what other examples can I give?
Or maybe can you elaborate on are we at the IEA like working on seeing if people turn the conditioner 2 degrees less or the heater 2 degrees more? Can we try to estimate the impact?
Yes, of course. So it's actually it's one of our current topic on which we are working on. So the first step is to, of course, understand the impact on energy demand. So when you changed by, for instance, 1 degree the temperature setting, how will it impact the energy demand? But of course, there are many aspects to behavioral change, because if it's a lasting change, it can also have an impact on the choice of technology as well. So everything is interlinked. But the first steps that we choose to follow is to focus on the impact on energy demand. So to focus on a short-term impact. So if we decide to reduce or increase for cooling the temperature setting, how much will we save? How much energy will we save? So these are the main aspects of behavioral change for in the building sector, because with appliances we cover almost everything that we can do in buildings without changing the well-being in a household. So, for instance, we didn't want to impact cooking or refrigeration needs, because we estimate that they are necessary for the household and we don't want to change them.
Just hello, everyone. One quick thing to add on that, we also look at, say, the energy demand reductions that can come from things such as changing the temperature in your washing machine. So as Ariane was saying, this doesn't impact your provision of services because you still have clean clothes at the end. But if you lower the temperature, then you can use less energy to achieve the same result. So we look at these sorts of analyses as well.
And while other participants ask their question, maybe one additional point on cooking. This is an area where it's very difficult to accurately estimate the human preferences because, as we all know, people have different equipments or fuels for meeting different cooking needs. And there is a practice that is called fuel stacking, where at home you can have LPG, but also rely on a charcoal stove for certain recipes. So this is about human preferences, which are very hard to model. And when we do the technology and fuel allocation, which is based most usually on least cost analysis, taking into consideration those human preferences is something very challenging but very interesting, and that can help get a better understanding of the energy consumptions.
Yep, absolutely. It's something that's can be quite difficult to integrate into buildings energy demand modeling because most of the input information that we have is on the primary fuel that people use. And so, for instance, when surveys are conducted amongst the population, people will be asked what is the primary fuel that they use for cooking. And so this is the information that comes through to us in our modeling. But then we might see that in a certain country, the average energy use per capita could be much lower than in a different country, and that might be because in one country people are stove stacking, so they might be using their improved cook stove using biomass for certain meals where they require a hot flame, but they might actually be using an electric rice cooker for part of their cooking needs as well. So these are obviously things that are difficult to integrate into the model, but we nonetheless need to understand in order to make sure that the solutions, the technology solutions that we push aren't purely based on what's cheapest or based on what's cleanest or these sorts of considerations. We also need to think about what are the local preferences. And so, for instance, in areas where a lot of cooking is done with an open flame, and so there's lots of grilling or high temperature flame use, then we need to be thinking that perhaps a solution that uses flames such as LPG is much more suitable than switching to an electric solution. Whereas in countries, for instance, looking at Southeast Asia, where there's a lot of rice cooking, then certain studies have shown that, say, switching to an electric rice cooker is much more feasible. So these are the sorts of, I guess, social things that usually are more based on expert judgment rather than bringing numbers into the model, but we need to make sure that we're taking into account this stove stacking.
Thanks a lot, Tim, for those additional inputs. Maybe there was a first question referring to a slide. I think I can come back to this one, asking maybe for clarifying again what structure means. So I don't know, Tim or Varian, if you just want to very, very briefly explain again between activity, structure, and performance, how this is structured.
Ariane, I'll let you take this one.
Well, okay, I can start and you can add some examples or other informations. So the activity is linked to the level of energy service demand. So for instance, for cooling, it's relates to the demand for cooling needs. So how much do we want to cool our flat or floor space for an household? The structure and performance are more related to the equipment, to the technologies that we use for a given end use. So for instance, for cooling. So the structure will be linked to the type of equipments that will be used for cooling. So what type of air conditioners. And for each type of air conditioner, we have efficiency, and the efficiency corresponds to performance. So activity is linked to the level of energy service demand. The structure is linked to equipment, technologies, and performance is linked to efficiency.
Perfect. And I guess I can just provide an example. If we think of water heating, for instance, then activity, so the demand for hot water would increase if there's more people in every household or if there's more households. And so we need more liters of hot water. So that's the activity effect, that change in demand for hot water as an energy service. And then, as Ariane mentioned, the structure and performance is more linked to the technologies that are chosen to provide that hot water demand. So the structure will be what fuels are chosen. So for instance, the structure, we can say the structure of water heating energy demand would be changing if we're switching from using purely wood for water heating to using some electric water heaters or solar thermal water heaters. And so that's some structural shifts in how we meet water heating energy demand. And then looking at performance, as Ariane mentioned, that's the efficiency, so the technological performance of each technology that's providing your hot water. And so we could have a different level of performance for different types of electric water heaters. For example, we might have just a resistance water heater, which is around 100% efficiency, or we could have a heat pump, which is also using electricity to provide hot water, but could have an efficiency level of a coefficient of performance of up to around 250% or higher. So I guess that's a real world example.
Thanks, Ariane and team. We have one last question before we close, so I will read it. It's known that the energy projections is a kind of strategic views towards energy parameters, and that's indeed we are trying to make this exercise something useful for having a strategic view and policy making views on the future of the energy. And the question is, what are the references or threshold we should consider like possible calculated errors in our estimation and calculations to the figure? So if I maybe I can start, and Tina, Ariane, please jump on it. I think what we've tried to show is that to have the most accurate and the best possible projections, we try to disaggregate and to understand from the activity variables to take proxy variables, but then of course you need to be pragmatic and to do with the data that you have at your disposal. There are different methodologies, and you have seen that you can use very simple estimations, making projections based on historical trends, also trying to make connections with proxy, as we've seen. And I think the idea is the point and the importance is to be transparent on your assumptions, on your exercise, so that you can be challenged, you can improve by discussing with peers who can help you develop your modeling tools.
Absolutely. And I think linked to this is the question of what are we trying to achieve or show with our models? So for instance, if we're trying to produce a forecast of energy demand, then yes, it can be very important to try and calculate the different errors along the processes. So then with our forecast, we have an associated estimation of the range of error that forecast has. But at the IEA, and especially in the World Energy Outlook work, we do scenario-based modeling. So rather than trying to just project forecast energy demand, we're looking at different scenarios. So rather than worrying about or looking into the error margin of each scenario, we're more saying that under a given set of circumstances, so it might be a given set of policy circumstances or economic circumstances, this is what a possible future could look like. And so in that instance, it's less important to look at the specific errors all the way along. We're more saying that given these assumptions, this is what the end result looks like. And then obviously we can run scenarios with different input assumptions to get a better idea of the impact on the final energy demand. So a very important thing to consider, and it obviously comes back to the philosophy, the objectives of what you're trying to achieve with your modeling.
If I may quickly add on that, So of course, please keep in mind that by 2050, for instance, it's really impossible to do forecasts. So as Tim mentioned, the philosophy here for energy projection is usually to use scenario and to do what if also analysis. And you can also, of course, do some sensitivity analysis to see what will be the impact of a special input and the variation of this input on your results. But you have to keep in mind that it's only projections and absolutely not forecasts.
Thanks, Tim.
And I see.
Ariane. No, please go, Tim.
No, I was just seeing some other questions pop up, but
Yeah, just very, very briefly, as time is running out, maybe we can say that tools and softwares for modeling energy demand. You've seen an example with Excel being able to make some interesting calculation. And the idea of this program is also to work with you Ethiopian experts on maybe developing new or adapting existing tools to help you make long-term projections of the energy system. And after this introductory online course, when we will be together in Addis for in-country trainings, we'll be able to work more in the tools directly. And maybe to take the other question, and Tim, feel free to add on that. There was a question on non-residential floor area. Just to say that today's presentation has focused a bit on household, and we've discussed in depth space cooling or water heating. But what we've done here, the idea is
events
to
and
do
modeling
it.
software.
Sorry.
But there's many options there, and Excel is probably the best place to start.
We lose your Arno for the last minute.
Can you hear me now? Yeah, no, okay, no problem. Thanks for having filled the silence. Just to say on the question regarding non-residential floor area, we focused the exercise in this presentation on household, on floor, on space cooling or water heating. But what we have done here, we do it for every energy sector, subsector, energy needs, and this is this bottom-up exercise that will enable us to get a view on the total need for electricity, for other fuels. So this is today was an illustration with the residential sector, but this is the type of exercise we do for each demand sector, and that make the IEA modeling comprehensive. And again, when we work together in Ethiopia, we can decide to work deeper on building or on transport or on industry, and to have the same approach as what we did today. So unless Ariane, team, you have a last word, just want to thank every participant for their attendance today and attention. Thank you very much to all of you, Zakia, Team, Ariane, for your presentation and your answers to the questions. And we'll see you on Monday, same time. And on Monday we will look more at the power sector and how to model the power sector.
Thank you. Bye, everyone.
Thank you. Bye-bye.
Thanks a lot. Bye.
Thank you. Bye.